problems. We're going to do problems 616 and 620 from your textbook. And we're going to go through this pretty quickly, so I hope that this vodcast is only about 20 minutes long. So we're going to start with 616. So we're going to look at your textbook, and you'll see the problem is that for a certain two-dimensional flow field, U is equal to 0 and V is equal to capital V. So the problem asks us what are the corresponding radial and tangential components, and determine the stream function. So basically what we have here is a problem of converting radial into radial and tangential components from Cartesian coordinates, and then determining a stream function, which we know is that del u del y is equal to u, and del psi del y is equal to u, and negative del psi del x is equal to v. So this is a little exercise in converting back and forth between radial and tangential components. So I've drawn just a basic grid of x, y, and the relationship between the velocity in the radial direction and the velocity in the theta direction. The velocity, this is actually should be parallel to this because v is equal to little v, which is the velocity in the y direction. So I've redrawn it here a little bit more clear, where v, the velocity in the y direction, is parallel to y because it's all y, and then vr is going this way and v theta is this way with the angle theta. Well, the basic conversion between radial and polar coordinates, when we have this y, is that capital V, which is the velocity in the y direction, times the sine of theta is equal to v sub r, and capital V times the cosine of theta is equal to v sub theta, because the angle is opposite and adjacent to the velocity vector. So this is part A. Part B, we have the stream function, which we know that del psi del y is equal to u, and we're told that u is equal to 0. So that's not really useful at this point. However, in the other direction, we know that negative del psi del x is equal to v, and we're told that that value is capital V. So if we take del psi del x, set it equal to negative little v, which is, of course, capital Z in this case, or capital V in this case, we can then integrate or take the antiderivative, and in Cartesian coordinates, express psi then is equal to negative Vx plus c. Now in polar coordinates, using this relationship only with x, we know that x is going to be equal to the cosine of v times the cosine of that angle. So we can say r times the cosine of theta is equal to x, and we can just plug that in here and say psi is equal to negative v r cosine theta plus c. And so this is really just an exercise in determining what that looks like, in doing a conversion between polar coordinates and Cartesian coordinates. All right, now the next part of our problem, the next problem that we have is 1620. And 1620 looks like this. Oh, I'm sorry, I've got to put up my camera. There we go. All right, so 1620, we have a two-dimensional, incompressible flow field, and we are told that the x component of the velocity is 2x. It first asks us to determine the corresponding equation for the y component of the velocity. All right, well, what do we know? We know that if it's incompressible, put back on the document cam, to satisfy the continuity equation, we know that del u del x plus del v del y has to equal 0 for an incompressible flow. All right, so we know that u is equal to 2x, so del u del x is equal to 2, just by doing the differentiation with respect to x. So based on the continuity equation, we can see that del u del x equals negative del v del y, or we could say that del v del y is equal -2. So if we separate, we can see then that v is equal to -2y plus some function of x. Now this is analogous to a constant of integration, but it's not a constant because since we have this as a partial with respect to y, if we had a term that was a function of x only, it would differentiate to 0. So we have to keep in mind that we have that it could be a function. However, it tells us in the problem that v is equal to 0 along the x-axis. So I should say since v is equal to 0 along the x-axis, that means what happens on the x-axis? Well, that means where y is 0. So that means that the function of x must be 0, and therefore v is equal to -2y. All right. So the good news is we have an expression that tells us, it asks us just for this value right here. We could write the velocity vector as u plus in the I direction plus v in the j direction. Right, so that's an expression for a velocity vector. It's a little more than they asked for, but that's okay. All right, the second part says, for the flow field, what is the magnitude of the average velocity of the fluid crossing surface OA? And this is what we have, right? We have point A up here at 1 and 1 in feet, and we have it at 0, 0. Well, what do you see here? At every point on OA, we have that x is equal to y. All right, and it's a straight line. So that kind of simplifies our ideas here. It asks us for the magnitude of the average velocity along that line. Well, since we have this velocity equation, we know that the average velocity is the square, using the theorem of Pythagoras, of those two terms, since it's a two-dimensional flow field. So if we simplify that, we get 4x squared plus 4y squared. The 4 can be factored out, and we get 2 times square root of x squared plus y squared. But we also know that on this line OA, x equals y. So let's just call it r. Just because I don't want to use z, because then that makes it look like it's a z-directional thing. And r, it really is kind of an r based on the idea that it could be a radial component. So we can say 2 times, instead of x squared plus y squared, we'll say r squared plus r squared equals 2 times the square root of 2r squared. And here this r will factor out, and we get 2 times r times the square root of 2. All right, well, what is r? It's x and y, and it's the same. It starts at 0, and it ends at 1. So if we were to find an average, we could find, since it's a straight line, we could find this value at 0, find this value at 1, and divide it by 2. So you can say 2 times the point 0, which is 0, square root of 2, plus 2 times this point A, which is 1, times the square root of 2, divide by 2. This goes away, this cancels this, and I get the square root of 2, and that's in feet per second. All right, so that's it for Vodcast 19A. We've worked out the 2 problems. Actually, we've worked out the 3 problems that we needed to have worked out. And the last Vodcast that we'll have, Vodcast 20, we'll cover the Navier-Stokes equations and a few solutions to a very theoretical partial differential equations. So we'll see you for 20.